Hello, I'm Hugh Manfield and welcome back to the Fluid Space Theory Lectures. Now today's topic is cosmology, and this is the 10th in the series and the final video of the core theory presentations. So the best theory at present is what's known as the Standard Model. And the Standard Model tells us that 5% of the universe is made out of normal matter, 27% of the cosmos is made out of dark matter, and 68% of the cosmos is made out of dark energy. So what we have is 5% known, 95% unknown. So what's wrong with this picture? If I was trying to solve an engineering problem and I had to use a 95% fudge factor, stuff that had to be made up to make the basic equations work, I'd be embarrassed. If I presented it to a client, I'd probably be fired and never hear from that client again. But physicists around the world proudly proclaim this model as if they've achieved something amazing. Well, it's not amazing. It's actually kind of ridiculous. Maybe you should try paying 5% of your taxes to the IRS and then tell them that, well, between dark matter and dark energy, it actually adds up to 100%. I mean, with the brightest minds around the globe working for 100 years, is this really the best you can do? I know what they will say is, no, Einstein's field equation works perfectly with this amount of dark matter and dark energy. Well, you know what? If that's what it takes to make Einstein's field equation work, then there's something wrong with Einstein's field equation. And it's time to start looking at some new ideas and some new answers. And that's just what I've done. The best way I have of summing this up is, if someone served you a sandwich and told you they didn't know what 95% of it was made of, would you eat it? I wouldn't, and it's time we stop eating the dark matter, dark energy sandwich. So what does fluid space theory tell us about cosmology? Well, to understand that, we start with the example of a space train. Now, space trains can be tricky, and it's easy to make mistakes. So I'm only going to use the aspects of the space train analogy that apply to the fluid space theory cosmology. So we start with our space train at rest at the station. All the cars are not length contracted, they're at their normal length, and the clocks on board the train are running the same as the clocks on the station. And we have Stan perched up on the top of the last car. And one other thing, each car is equipped with a strobe light that flashes once per second at a known frequency. And the cars are actually 1 light second long. Now 1 light second is about 2/3 of the way to the moon. So I've scrunched them down to fit on the sketch. So the space train leaves the station and starts building up speed as it crosses the galaxy. When it gets to about 71% the speed of light, it's going to be 50% length contracted. But Stan, riding on board, won't see that length contraction. He'll see the train as being its normal length. And if he has a measuring stick, he can measure the length of the car, and it's going to come out to him the same length that it was when he was at rest at the station. And as the train continues on and gets up to its top speed of 97%, the speed of light, it's going to be contracted down by 95%, and it will only be 5% of its starting length, at least to an observer at the platform. But we know what the other 95% of the train is. In this case, it's been length contracted off into the TC dimension, and as far as Stan is concerned on board, everything's still normal. He can measure the train car that he's in, and it still measures the same length to him that it did when it was at rest at the station. Now, the train is also going to be time dilated. So, when the train is at rest at the station, a clock on board the train will keep time in pace with the clock at the station. And when the train is 50% length contracted, the reciprocal in time dilation is going to be doubled. So for a clock that ticks off 1 second on board the train, the station clocks will tick off 2 seconds. And when the train gets up to top speed, a second on board, the train will take 20 seconds to tick off on the station clocks. So our space train travels across the galaxy and it's getting near its destination, where it starts to slow down to arrive at the station, where it will come to a stop. So as it slows down, someone on the station platform observing will see the length contracted train expand out as it slows to its full length as it comes to a stop at the platform. So what this means to Stan on board is that he is immersed in an expanding space-time, at least in the direction of the motion the train is traveling. And what he's going to see is that as the photons arrive to his perch on the last car of the train, they're going to be 1 second old, 2 seconds old, 3 seconds old, and so on. And the Old News Aberration comes into play. So what's going to happen is that Stan's going to see an after image of those strobe lights, and he'll see them as they were in the past. And in the past, as the train slows, the train was moving faster. And since it was moving faster, those strobe lights were more time dilated. So he's going to see red-shifted photons arriving from those clocks and from those strobe lights. And it's going to increase in proportion with the distance. So what Stan's going to see from the end of the space train, it's kind of like the same thing we see when we look at distant galaxies. The farther he sees into the distance, the more red-shifted the strobe lights on the train cars are going to be. And this is caused by the Old News Aberration. In reality, if Stan were to travel down all those cars, his clock would match the clocks on the other cars. His meter stick would match the meter sticks on all the other cars, because he's co-moving with that system. But he's seeing it due to the distance involved. He sees the old news of the clocks and strobe lights as they were in the past while the train slows. So the main thing to take away from the space train analogy is that Stan, riding on board the train as a passenger, will not see the effects of length contraction or time dilation. The train will seem to him to stay at the same length throughout the journey. So if we look at our unit cube and we set it into motion, and it becomes length contracted and time dilated. Now this is what's happening on board the train. I want to take that analogy a little bit further, that let's take a unit cube, and in this case, instead of setting it into motion, we increase the level of vacuum energy in that unit cube. And what we're going to see is that the unit cube will contract in all dimensions and become time dilated. So it's very similar to what's happening with Stan on the train. He's moving from a higher energy reference frame to a lower energy reference frame from the point of view of the station platform. And we have the unit cube. If it's at a higher energy level, it's going to be smaller, length contracted and time dilated. And if we reduce that vacuum energy, it's going to expand out to a larger, less time dilated size. So now we've put Ricky and Stan inside the glass box, and they're playing a game of catch with the football. And then in the first case, we have a very high vacuum energy, and they're going to be length contracted in all dimensions and time dilated. So if we lower that vacuum energy, they will become less length contracted and less time dilated. Now, from their point of view, inside the box, they're not going to notice any of this happening, because they're like passengers on the space train. They're immersed in the expanding space, and they don't see the effects of length contraction or time dilation. And if we reduce the vacuum energy even more, the box expands back out to a larger size, and the clocks speed up to a faster rate. And it could be that it's not Ricky and Stan in the box, but maybe we have an entire galaxy. And the same thing would apply. The galaxy would remain in the same proportion relative to the box we've put around it as we lower the vacuum energy. And the clocks within the galaxy would increase in pace as the vacuum energy decreases. And anyone living in that galaxy would have no idea this is happening, and they would see no effects at all. And we could even put in a galaxy cluster or a large chunk of the cosmos containing many, many galaxies, and the same thing would be true. Except the one thing that we begin to see, the larger this box becomes, the more the old news aberration takes effect when viewing objects from one side of the box to the other. And if we had a large chunk of the cosmos inside this box, then the old news aberration would cause any observer from any location looking out to see galaxies in the distance redshifted with increasing distance. Now, the thing to note about this model of cosmic expansion is that it doesn't require some unknown energy source to drive it. It's driven merely by the loss of vacuum energy over time, which would be a natural process. So the redshift we see when Ricky looks out at a distant galaxy is merely the old news aberration at work. The clock on her planet, within her solar system, within her galaxy, are all running at the same rate as the clocks in the distant galaxy are running in the present moment. However, we're seeing an after image of that distant galaxy, and we're seeing it at a time earlier when the vacuum energy of the cosmos was higher and the clocks were running slower. So the light we see coming from that galaxy will be redshifted. So now, thinking back to the antimatter video, we take a look at the cosmic microwave background. And if we assume that the orange areas are where normal matter collected and the blue areas are where antimatter collected, then the redshift becomes a little bit more complicated in computing a distance to another galaxy. For example, if you're observing a galaxy across this blue void, it would be filled with antimatter, which is expanding. So the photons would be shifted to the red by the loss of vacuum energy in the overall cosmos, plus they would be shifted to the red due to the expansion of the antimatter expansion field within that void. So you'd have to account for that in computing an accurate distance. And the same thing is true if you're observing a galaxy through a region dominated by primarily normal matter. That would be surrounded by a contraction field. So a photon traveling through that distance would be redshifted by the loss of vacuum energy over time of the cosmos at large, but it would also be blue shifted due to the contraction fields that it's passing through. So computing distance with redshift got a little bit messier for cosmologists. So now I'd like to spend a little time summing up the first 10 video lectures. What has fluid space theory shown us? Well, it shows us a cosmos that expands as vacuum energy decreases, which is a natural process, and there's no need for some unknown dark energy to drive that expansion. It shows a cosmos that expands without getting bigger. And what this means is that we'll always look out on a galaxy-rich cosmos, and that there's also no Hubble horizon. In the fluid space theory form of expansion, there's no horizon. There's no limit on how far we can see a galaxy, except for the amount of time it's going to take the light from that galaxy to reach us. Fluid space theory tells us where the antimatter went. We could probably find that antimatter is in the large voids as a thin soup of anti-hydrogen gas between all the galaxy clusters. But the best of all, it's a cosmos where 100% of it is known. So in conclusion, there's no need anymore to eat the dark matter, dark energy sandwich. There's something better, and it's called fluid space theory. And it explains the cosmos in a way that is much more easily understood, in a way that you don't have to use a lot of fancy, indecipherable physics speak, and in a way that doesn't involve using a lot of bewildering math, and it's within the reach of just about everybody on the planet. So hopefully you'll like this video and help spread the word. Until next time, I'm Hugh Manfield.